All right, guys, well, welcome back to the videos. I've got our last video ready to go. We're going to be talking about parallel resonance on this one. This one's a little bit more complicated. There's just a couple of extra steps, but the whole idea is the same thing, is we're looking for our resonant circuit at where the reactance is going to be the same. And in this circuit, we're going to have a special device that we call, basically, a special configuration that we call it as a tank circuit. Now, once we get going here, we're just going to cover the tank circuit very, very briefly. Later semesters, it's going to become a lot more important as to what we're looking for with this guy. He's used a lot in the RF fields. It's also used to build an oscillator. It's one of the things we use to help pick out which frequencies and stuff we want. That's usually where we change stuff. But anyway, like I said, we're gonna learn the very basics about what the tank circuit is, and then we're gonna go through the examples of try to figure out which is the band pass, which is the band stop configuration, and then after that we'll go through an example like we have in the homework. So we'll kind of show like I said, we'll go with those. And as always, please, if you have questions, write them down while you're watching the video, and then you can ask me later. I will be available, like I said, as always, during our normal lab and theory times from 8 to 11 and 1 to 3. But if you do need help outside of those, please feel free to let me know, and I will do what I can to help you guys out whenever you need it. Um, so let's go ahead and just dive right into this. So we will start off here with parallel resonance. So the basic circuit that we have that we need to kind of have an idea with is it looks like this. Now physically we can't separate out the winding resistance from our inductor, but for this purpose we're going to list it as a separate to talk about these guys. So in a perfect situation, in a perfect world, our winding is going to be equal to 0 ohms. It's going to be perfectly, just the inductance. That's all we care about. That's what we need. But we don't live in a perfect world, unfortunately. And so what it does is the winding resistance does exist, and so we need to take that into account with our when we're doing these conversions. So one of the things that we have to do is to be able to separate this out, so we have just inductor and just the capacitor in parallel. That is our tank circuit. It's just pure inductance, pure capacitance. So we have to be able to mathematically remove the winding resistance out from a serial, and we're going to give it a parallel equivalent. Plus, this is also going to make this circuit a lot easier to solve when it actually comes down to getting the actual calculations for, the total impedance and a couple other things, because it's going to separate everything out into just our plus and minus 90 degrees and our 0 degree angles, which when we have those, we can take those and we can quickly convert back and forth between capacitive and reactance. Between polar and rectangular notation when we're at plus and minus 90 and 0. So like I said, that's the idea that we have behind this, but the only problem is this only works and it only exists when we're at our resonant frequency. So that's kind of the idea. So what we're going to do here is we're going to take this circuit and we're going to convert it into an equivalent circuit to where we have these guys here and our capacitor. So we have our L, we have our C, and then this is going to be our R equivalent. And so like I say, the whole idea is we're moving our winding resistance and we're converting into its parallel equivalent to look at the circuit, because this has a couple of special cases of what goes on when we have a tank circuit. So as we're looking at this, a couple of things are going to stay the same. Is we're going to still have our Q point, and that is going to be equal to the X of L plus our R winding, because most of the time we're not going to have another resistor in here, but later on if we want to adjust our Q point a little bit, we can add more resistance, and so we would just put that in series with this inductor. But to start with, all that we have in there is just the winding, so that's all we're going to look at right now. Our R equivalent is going to be equal to the resistance of the winding that we have multiplied by Q squared plus 1. And I'm not sure the exact origin of these equations, but this is what we got to use to work these problems. And when we work them, these are what the values we're going to see based on them. Like I said, when we'll do a couple examples, as we figure out which configuration we need to achieve bandpass bandstop, and you'll kind of see that this is where it's going to split. And then if you hook this up and measure it, you're going to see the exact same thing. All right, so our equivalent we have, and then we also have the L equivalent. So we have to convert both the inductor and the resistor into its parallel components. And the L equivalent is equal to our Q squared plus 1 divided by Q squared. So basically what this is going to do is it's going to give us a value that's just slightly higher than our inductor. And one of the things that we don't have to take it into consideration, when we're doing our calculations later, as long as our Q point is over 10, which most of the time it will be, it's not going to make any difference in the calculations for when we go through and solve this guy. So we're just going to go with it at that. Like I said, most of the time we're going to have this over, the Q point is going to be over 11. Remember, that's our quality factor. That determines our range of frequencies, things like that. So that we have for those equations. Once we convert, so now once we've got this converted down, this right here that I'm outlining right now, this is our tank circuit. And so we have this guy. Now kind of a little bit more of a definition of this guy. So the tank circuit has a few special properties about it. Okay, it stores energy in the magnetic fields and it charges the plates of the capacitor. So it stores it in the magnetic fields in the inductors and stores it in the capacitor from its plates. And now when we have those, what it's going to do is it's going to transfer the energy. So the energy that it builds up in the magnetic fields, when that field collapses, it's going to induce a current, which is then going to charge the plates in the opposite direction. The plates are also going to discharge, which goes through the inductor, which then creates a magnetic field. So what this is doing is it's transferred the energy back and forth and back and forth and back and forth between our inductor and the capacitor. And in a perfect world, where we didn't have any kind of resistance, it would do that forever. We would basically have a perpetual energy machine. But now the problem is we have that winding resistance, so every once in a while we have to kind of recharge it just a little bit to keep the max voltage bouncing around. And so this tank circuit, so every half cycle, the energy that it's stored in the magnetic fields and then on the charge on the plates is going to switch. So every half cycle, the energy switches between the capacitor and the inductor. I guess not switches, transfers. So we get like a positive charge on the capacitor, then we get a negative magnetic field on the inductor. Every half cycle, we're going to see the capacitor discharge, and then the inductor discharge its magnetic field, and then we're going to see them flip-flop back and forth. And so that's where we get the cycling. And that's one of the big things that the tank circuit does, is it's able to transfer its voltage that it's stored in the charge and in the field back and forth. And so we get this nice clean oscillation coming out of our tank circuit, which we will use later on in different parts of electronics. Specifically RF is one of them, where tank circuits is quite heavily used. The other thing that we have is on the tank circuit, at resonance, so at our F of R, the tank basically acts as an open. So basically has an infinite resistance from those points. And so that's the other reason why we wanted to split this up to be able to have this equivalent. Because when we have at resonance our inductor and our capacitor, essentially those disappear. They go away. We don't even see them. And so what's left is their combined impedance, which is pretty much the impedance of the wire that we have left over. And so when we do this, we're going to see that value actually translated over. And that's why we measure what we're measuring, because of the phenomenon that we have where we're translating things back and forth between series and parallel, going back and forth. And so like I said, so yeah, at resonance, the tank circuit's going to act as an open. And so our impedance total for the tank is going to be equal to essentially our resistance equivalent. And the cool thing about it is since the capacitor and the inductor are essentially removed from the circuit, now we're down to a position where we should have very little, if any, phase angle. We're looking at 1, 2, 3 degrees maybe with just the residuals when we actually go into calculate the LEQ and all that. But what we have here is very, very little phase angle, so we should be seeing a 0 phase angle on everything coming out with the currents and the voltages and things like that. And then also we should see a little bit of and we'll see a drop between what resistor we have coming in and the source and things like that. So it's something to be aware of. If we want, a bigger output, depending on where it is, we'll have to increase resistor sizes, things like that, decrease the capacitor inductors, stuff like that. Find more inductors that are better as far as having less resistance to get more inductance, that kind of thing. So one of the things to note, and this is very important, that our REQ, the LEQ, and our Q point only exist, are only valid, not exist, they're only valid when we're at our resonant frequency. So when we start changing frequency around from what our resonant is, we no longer can calculate the Q point. Like I said, it gets into the more of the calculus based of very complicated drawn out numbers that it takes quite a while to calculate it. And it's not very accurate at that point because our slope's constantly changing depending on where these guys are changing. And so we basically only count Q is at our resonant point. And then because our R equivalent and our L equivalent are based on Q, they're not going to exist and we're not going to use them other than our critical frequency. So like I said, the critical frequency is going to be one of our hot topics for where we want to be. All right. So the next thing that we have that we want to look at is with this kind of in mind, let's take a look at a LRC circuit with our parallel system in our tank circuit, basically is what I'm trying to say. And then we're going to kind of make a determination. We'll run through a quick example and we'll make the determination on which one's which as far as band pass, band stop. So remember that we have our high pass, low pass. So they're going to look like this. This is our critical frequency. We have filters that look like this. That's our critical frequency. So this is a high pass filter. This is a low pass filter. And we can get those combinations based on the L and C and L and R combinations, depending on where we take the output. And then the other types of filters that we have, this is the band pass. And this is the band stop. So this is the two that we're going to be dealing with, the band pass, band stop, based on this parallel configuration of our of our inductor and capacitors. Okay, so the circuit we're going to talk about is as follows. So we have our supply, and we have our resistor. And we have our capacitor. There's our ground. This is V out. And then versus this guy, like so. So again, we're isolating between our reactive components and our resistive components. So we got R, L, and C, C, L, and R. And the values that we have, so we have a 56 kilo ohm resistor. We have an inductor at 2.4 millihenries and 132 ohms of winding resistance. And our capacitor is 330 picofarads. So this is the example we're going to go through, and then later we'll go through and fill out the last little bits of information like in our homework based on the same problem. That way we can reuse the numbers and don't have to create quite as much. So that is the circuit we're going to be working on. And now what we want to know is just real quick is we want to do a comparison. So I'm going to draw out my little chart here. So we're going to have at our resonant frequency values that we're going to look for. We're also going to have our resonant frequency divided by 20 because we want to go way lower and way higher. And we have our resonant frequency at 20 times. So the things we're going to be looking for, we're going to be looking for the reactance of the capacitor. We're going to be looking for the reactance of the inductor. We're going to be looking for R equivalent when it's appropriate. We're going to find the Z tank for all of these guys. We have our R1 value as a comparison, the impedance total of the circuit, and then the current total. And last but not least, we're going to look at the voltage out when we go across the resistor and the voltage out when we go across the tank. So let me just flush out my chart, get everything nice and organized. All right, so now that we got those, let's go ahead and start calculating this guy. And as always, we want to start at a resonant frequency that kind of gives us the basis for everything that we're doing. So the first thing that we are going to want to do is we want to decide, like I said, we want to decide which one's which, the band pass or the band stop, based on these two configurations. So as we get into this, let's solve everything based on our resonant frequency first. And I will do this guy in red. And we'll stick with black. So at our resonant frequency, well, the first thing we need to do is calculate what those values are. So the first thing we look at is our resonant frequency. The formula to find that is the exact same as our series. So it's 1 over 2 pi times the square root of the inductance times the capacitance. Okay? So as we put that in, we end up with 1 over 2 pi times the square root of 2.4 milli and multiplied that by 330 pico. Square root of those values times 2 pi, take the reciprocal of that, we end up with a frequency of 178,837 hertz. So there is our frequency that we're going to be solving for. Now the next thing we want to do is we want to solve for the Q point because we're at resonance, so Q point exists and we need it to solve for our equivalencies. So the Q point is equal to the inductive reactance over the resistance of the winding or any other resistance that's in series, direct series with the inductor. So in this case, we need to find what the X of L is for this value. So we take our X of L is equal to 2 pi times our frequency times the inductor, and the frequency we're at is up here, this 178,000. So we have 2 pi times 178,837 times 2.4 milli, and that gives us a value of 2,697 ohms at positive 90 degrees. Okay, so now that we have that, we can calculate our Q point based on this, so we can convert our circuit to its equivalent. So we can look at it and analyze this just as a LRC or as a L resistor in parallel with an inductor in parallel with a capacitor. So this is what we're trying to do right now, is convert this guy into this. Like that. So this is our R equivalent, this is L equivalent, this is our capacitor. And like I said, this will make sense for why we're going to do this and how it's going to make it easier for us to calculate this. All right, so the first thing that we have is we need to solve for the R equivalent, and that is equal to the resistance of the winding multiplied by Q squared plus 1. So R equivalent is equal to 132 times, our Q, which we didn't calculate because I jumped up ahead a step. So our Q, we're going to jump back here, so it's 2697 divided by the 132, and that gives us 20.432. Now remember earlier when I said if our Q is over 10, we don't have to worry about the L equivalent. It's not going to make much of a difference. So now when we plug this in, we have our, this value is not going to make much of a difference for our inductor. But for the equivalent, we still have to take that into account for the R equivalent. So we have 20 squared plus 1. And this value comes out to be 55,238 ohms. So now we have this done. And remember, so now that we've got it at this point, we have just pure inductance and just pure capacitance, which means these two guys are going to completely cancel them out, and we're going to be looking at this. We have our R equivalent and essentially an open, our tank circuit, as far as the impedance goes. So it's not even going to play. And even if we were to throw in some insane number, you know, like 250 mega ohms, just throwing that out there, versus the 55,000, we're going to get 55,000 ohms of total resistance in parallel with each other. So with that, we can ignore it because it is essentially an open. And now we need to solve for the Z tank. So our Z tank is just this open, so it's going to be equal to the R equivalent, because that's all that's left in here. If we were to hook up an ohm meter, that's all we would see at that point, is just this 55,238. So we have 55,238. So now, the thing we have to look at and have to realize is, so now that we've looked at this with our Z tank and when we're trying to find our Z total, so one thing to look at is if we go for Z total, it's going to be equal to our resistance plus the Z tank, which both of these are resistive values because there's no reactive components whatsoever. They canceled each other out. We're just going to be able to add these guys together. And one of the nice things too is because we don't have to worry about a phase angle or anything like that, now we can go back and use voltage divider, which we haven't been able to use for a while because of the phase angles. So it's going to simplify this problem to solve the voltage out for this guy. So since we do that, we don't even have to worry about finding the current now because it's going to be just this value. So we're going to solve for the voltages across our resistor, and we're going to solve for the voltage across the tank. So with the voltage across the tank, we're using voltage divider. We have the 55,238 divided by the 55,238 plus the 56,000. We multiply that by our voltage in, which, did I put that on an original formula? I did not. So we have 52 volts across this guy. So I forgot that part. So the voltage out tank, we take the value of the impedance of the tank divided by the impedance of the tank plus the resistor, divided by, or multiply that by 52 volts. So V out tank at resonance is going to be equal to 25.822 volts. And then the V out of the resistor, we take the 56,000 ohms, we divide that by the 56,000 plus the 55,238. So like I said, this is just voltage divider that we learned a while ago, multiplied by the 52 volts. So V out from our resistor is going to equal 26.178 volts. Now in the previous examples, like I said, we have a kind of a conundrum here that we're looking at. So we have 52 volts going in, but right now we can only get 26 volts coming out of our resistor. And that's just based on the properties of the inductor. So what we're going to see is in this situation, this is going to be the max voltage that we have across our resistor. This is the best point to get this voltage. So when we do our decibel conversions for the different frequencies and things like that, it's going to be based on this 26.178 volts. That's the highest that the resistor can ever get to, because even if we look at something else, that's that's the highest it can get to. Excuse me, that is not right. The V out tanks, excuse me. And the reason we'll talk about this later is because as soon as we start varying frequencies, we're going to start changing this relationship between the impedance of the capacitor, impedance of the inductor, and we're going to start seeing one climb really, really high, while the other one in the parallel is going to drop really, really low. So when they're in parallel, they're going to be less than that. And so now where we're at, we have an infinite amount of resistance, so we're going to see just this equivalent resistor. But then once we start changing the frequency from resonant, it's going to be a smaller value, net smaller value, between what's now. So we're going to see this value across the impedance of our tank circuit drop, which is going to drop its voltage that it can have. And so, sorry, when I said this, the tank voltage, that's the highest we're going to be able to see it. This is the highest it can ever get because we've eliminated different components in parallel. But then when we start adding things back into it, the total resistance, total impedance of that circuit is going to drop. So sorry I misspoke. Like I said, it's the V out across the tank. This is the max voltage that can get. So now we have these values. And like I said, we're not too concerned, we're concerned with the angle, but right now what we know is at this value, the angle is going to be 0 degrees. Because we have, this is at 0 degrees. Our voltage is at 0 degrees. The current's going to give us 0 degrees. So all of these things are going to be at an angle of 0 degrees, which is one of the ways it'll tell us is if we are in phase or close to being in phase within 5 degrees or so with our signal coming in. So now that we have these values, let's go ahead and let's go back up and plot them into our chart just so we can keep track of these guys. So when we have our resonant frequency, we had an X of, so remember, at resonant frequency, X of C is equal to X of L. So those values are going to be the same. So we calculated one, we don't have to calculate the other. So we got 2697. That's going to be at negative 90. We have 2697. That's at a positive 90. The R equivalent we had was 55,238. And we're only going to have that at the resonant frequency, so we don't have to solve for it for the other two spots. We have our Z tank, which comes up to be 55,238 because there's nothing else in parallel with it. And then we have our impedance total, which was 111,238. So that's when we add the resistor and the Z total together. That's the value that we get there. So we got ohms, 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 ohms. That's ohms. The impedance total we got, this one is the 56,000 for a resistor. This is the 111,238 for the impedance total. The current total we didn't calculate because we didn't need to. The voltage out on a resistor was 26,178, and the voltage out on the tank was 25,822. Okay, so that's what we have for our frequencies. And let me go ahead and write this up there. So we got 178,837. The high end, we're going to go 3.577 meg. And we're going to go 8,942. So that's if we take a resonant frequency, we multiply it by 20, divide it by 20. These are the two ranges. Now, the reason I'm going 20 is I want to go really far out there so we can get a real clear definition and a real clear shape of what my graph is going to be looking like as we get to a lot higher frequencies, a lot lower frequencies than based on this resonant. Because we could go out and we could do, we have 178,000 hertz. We could go up to 180 hertz, 176 hertz, and just go out 2,000 hertz at the time. But I want a real drastic change so I can clearly see exactly what's going on with this circuit. So I always kind of figure, if you want a drastic change, go 10 or 20 times higher or lower than the critical frequency if you're trying to determine which, as an analysis tool. You don't want to be right, you don't want to have one data point right here and the next one right next to it. With what we're dealing with, we want value points that are out here away from the center frequency point. Okay, so now that we have that, the next thing we need to do is we need to solve this circuit doing the exact same steps at these two other frequencies, so we have at least 3 points of data that we can compare and look at to see what is my output doing of this circuit. How can I determine which one of these signals, either the band pass or the band stop, which one of these two signals is my circuit going to do in this configuration? So we'll come back down here. So this one I'm going to do in red. So we're going to do our resonant frequency divided by 20, and that's going to give me 8,942 hertz, just as a reference when we're going through these calculations. Let's see, so 2B, I'm just making sure I have all my notes in order. We'll keep that one handy. This one will flip over. All right. So the first thing we want to do is we want to calculate our capacitive reactance of the circuit. So our X of C is 1 over 2 pi times the F of C. And like I said, the reason that we're doing this is we're trying to find the total impedance of our tank circuit, which then we can solve. We can add that to the impedance of our resistor, so we can get our total current. Then we can use that to find the voltage drops across each of these components. That's the whole idea behind these. So we take our X of C, we find that. So we have 1 over 2 pi times 8942 times the 330 pico. Take the reciprocal of it, and that gives us a value of 53,935 ohms at a negative 90. We want to find our impedance of our inductor. So that is 2 pi times the frequency times the inductance. So 2 pi times 89. And we run that through our calculator. And we have that 2.4 milli. That's going to give us a value of 134.842 ohms at an angle of 90 degrees. Right, so now we're going to go through and we're going to convert this into the impedance of our inductor. So it's going to be the 132 ohms of winding resistance. For that equation, we're going to convert that into polar. So give me just a minute while I chug that through my calculator. Okay. So now when I plug that to my calculator, I get 188.696 ohms at an angle of 45.610 degrees. So we should be seeing, like I said, you can kind of double check. 45 degrees is when our real and our reactance values are equal. So we have that. So now we need to solve for the impedance of the tank. Get rid of our parallel branch. So remember, this is also our Z total for parallel that we found before. We're just calling it Z tank because of everything that, we want a tank circuit, so that's why we're labeling it as such. So to solve for the impedance of the tank, to kind of shorten this up, I'm going to use the product over the sum rule because there's only 2 branches. It helps speed things up and simplifies things down instead of doing the reciprocal method. So for the Z tank, it's going to be the impedance of the capacitor times the impedance of the inductor divided by the 2 of them added together. So we take the impedance of our capacitor, which is 53,935, and that's going to be at a negative 90. Multiply those two, the 188.696 at 45.6 0.610. We divide that by the impedance of our capacitor in rectangular form, and since it's at 90, we can easily convert that. So it's 0 minus J of 53935. And then we're going to add that to the value that we found earlier for our impedance for the inductor, 132 plus J, 134,842. So this we're going to add together and then convert to polar so we can divide it out. So we end up with, on this one, kind of just doing the steps all together, we end up with 132 minus J of 53,800. We're going to convert that to polar, and that comes out to be 53,800 at an angle of negative 89.859 degrees. So then we're going to take these two values that we have, so the 53,935 and the 188,696, multiply those together and then divide by this 5380. We're going to take the negative 90, add the 45, and then subtract the negative 89. So when this is all said and done, we do all this math. This comes out to be 56,132 at an angle of 0. Oh, sorry. Our Z tank, because remember, this is in parallel, so we got to remember, we have the 134, we have the 53. It's also in parallel with big equivalent. We're going to see, and because of these phase angles, it looks a little odd, but we have 189.164 ohms at an angle of 45.469 degrees. So now that we've gotten through there, we've solved it. Like I said, we can go back through, double check that math, but we're just taking the 53,935 times the 188,696, dividing that by the 53,800. We end up with 189,164 at 45 degrees, roughly. So now that we have that guy, we're going to want to take this and convert it into rectangular because we're going to add that value to our resistor because now these two are in series. So we convert that down. This becomes 132.66 plus J of 134.85. Our impedance total is equal to this value, the 132.66 plus J 134.85 plus our, so this is Z tank. We're adding that to our resistor value. So that's 56,000 plus J of 0. And so we end up with our Z total is equal to 56,132 plus J of 134.85. Convert that to polar because we're going to be doing division with it. And we end up as a grand total for our impedance total is 56,132 at 0.138 degrees. So almost 0 is what we're looking at. And so now that we have that, we can solve for the impedance total of this guy. And we're going to get, remember this is the voltage total divided by the impedance total. So we have 52 volts at 0 degrees. And then we're going to have the 56,132 at 0.138. And that gives us a grand total of 926.388 microamps at an angle of negative 0.138 degrees. Now, the reason I was hesitating is I was looking at this myself. I I have to make sure I have my brain wrapped around it, and sometimes I jump ahead on the steps on my notes. And so one of the things I was thinking of, just to explain my thought process, is I was like, oh, we're solving at our critical frequencies, F1, F2, so these should be closer to 45. But we're not. We've gone way outside of what our bandwidth is, and so that's why we're getting these weird angles. But these are what we should see in the circuits. Is we should see the farther we get out, we should start seeing less and less angles. Everything pretty much comes down to zeros at the end. And then at our 3 dB points at F1, F2 that's when we're going to see these 45. So that's what I was keep getting tied up on. And I was double checking my notes real quick to make sure I had it. But because we're so far out, we should be seeing these angles, they're not going to necessarily match with what we have. What we would normally get when we work these equations, because we're solving them at critical frequencies. These are just an example of extreme frequency plus or minus. Anyway, so don't worry about the delays. It was just me double checking to make sure I had this right. So we have our current total. So now the last thing we need to do is let's look at the voltage drop out across our resistor, and we want to find the voltage out across the tank. So I total times our resistor value. So we have the 926.388 micro at an angle of negative 0.138. Multiply that by our 56,000 ohms, and that is at an angle of 0. So the V out, so basically what we're going to see on our resistor at this frequency is going to be 51.878 volts at an angle of negative 0.138. So very, very negligible on the angle. We're not even going to see that. V out on the tank is going to be the 926.388 microamps, and that's at an angle of negative 0.138, multiplied by the impedance of our circuit of the tank. So 189.164, and that was at a 45.469 degrees. So when that's all said and done, the V out tank is going to be equal to a 0.175 volt drop. So very, 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 very small compared to the 52 volts that we started with. So now let's go ahead and take these values that we calculated and let's throw them back up into our table. So at our critical frequency, 20 times less than our critical frequency, we end up with 53,935 ohms across our capacitor. The reactance across our inductor is 134,842 ohms. We don't have an R equivalent because we're not at resonance. The impedance of the tank was 56,132. The resistance is going to stay at 56,000. The impedance total was 56,132. The current total was 926.388 microamps. The voltage out across the resistor was 51.878 volts. The voltage out across the tank was 0.175 volts. Now just remember, as a point of reference, we're just solving both cases for this circuit. We're either solving it for the voltage across the resistor or the voltage across the tank. So that way we don't have to go through these calculations twice, because a lot of them are going to be the same, and we can see what this is going to do. So now, the next circuit is, now let's solve this exact same circuit, do the exact same thing when we go through this, but now we're going to solve when we're 20 times our resonant frequency. So when we're at FR times 20, and that gives us 3.577 megahertz. The X of C value, 1 over 2 pi times the frequency times the capacitance. So we have 2 pi times 3.577 meg times the 330 picofarads. That comes out to be 134.83 ohms at negative 90. The inductive reactance is 2 pi times F times C. So that gives us 2 pi times the frequency of 3.577 meg times 2.4 milli. So I'm going to make sure that this is designated as a capital so we don't have any confusion. And that gives us a total of 53,940 at a positive 90 degrees. Now, because this inductor does have some winding resistance, we need to solve for the impedance of the inductor. So we have 132 plus J 53,940. Convert that into polar because we're going to be dividing it and multiplying it, we're going to be multiplying that value. So that is 53,940 at 89.86 degrees. Now we're going to find Z tank, impedance of just the tank circuit. So we're going to use, again, product over the sum. So Z of the capacitor times the impedance of the inductor over the impedance of the capacitor plus the impedance of the inductor. So we end up with 134.83 at negative 90, and that is multiplied by 53,940 at 90. That's going to be divided by the 0 minus J of 134.83 plus 0 plus J of 53,940. So those are the rectangular values for the impedances of those guys. We add those together, we convert it into polar. That is going to become 53,805. So I'll just go ahead and do this multiplication and get this converted, and we'll kind of do this all in one step. So we have the 7.273 meg at 0 degrees, and that's going to be divided by 53,805 at 89.859. So now that we have everything in polar, we have one value on each the numerator and the denominator. So our Z tank is going to be equal to 135.173 ohms at an angle of negative 89.859. Now we need to solve for our Z total. So we're going to add our Z tank plus impedance of our resistance. So we have 5,600 or 56,000 plus J of 0, and that's going to be added to 0.002 minus J 135.173. So when that's all said and done, Z total is equal to 56,000 minus J 135.173. That 0.002 isn't going to do anything, so we're just going to drop it. And we convert that into polar. Our impedance total of this circuit comes out to be 56,000 ohms at an angle of negative 0.138 degrees. So again, when it's all said and done, because we're so far out, our angles are 0. At our negative 3 dB points, they will be at 45 degrees-ish, plus or minus a few degrees. And then at our resonant frequency, they're at 0 again. So we have that impedance total. We're going to find our current total. So we take the 52 volts at 0. We divide that by the 56,000 at negative 0.138. That gives us 928.571 microamps at a 0.138 degrees. Voltage out of our resistor is the 928.571 micro multiplied by 56K, which is we're just undoing the previous step. So that's going to equal 52 volts on the money. V out across our tank is the 928.571 micro multiplied by the impedance of the tank, 135,173, and that's going to give us 0.125 volts. So now that we have everything solved, let's go back up and we'll put everything into our table, and then we'll kind of take a look at the table and analyze what we have. We'll graphically draw out what happened in our graphs or with our data. So at 20 times the resonant frequency, the X of C ended up being 134.83 ohms. The reactance of the inductor ended up being 53,940. The impedance of the tank was 135,173. R1 stayed the same at 56K because it's not affected by frequency. The impedance total came up to be 56,000. Okay, and now the current that we have is 928.571 microamps. And the voltage out across the resistor is 52 volts, and the voltage across the tank is 0.125 volts. So now let's take a second, let's going to analyze what happened on our chart. So we have 3 points to take into account, and we're going to draw these out to show what everything did. And then we'll kind of make the inference, and then we will label which output is which for a band pass or a band stop. So real quick, we have our graph. So this is our frequency, and we have voltage here. So we know we're going to have a mark up here that's 52 volts. We're going to have a mark about halfway in between because we know we have a 26 volts. And then we've got our 0. Okay. The frequency ranges, we're going to label them just as our FR. We're going to label it as 20 times FR. And we're going to label it as FR divided by 20. So we could put the actual values in there, but for right now it's just kind of a representation of what is happening on this chart. So let's take a look. Let's put in, I'm going to use red, so we're going to use our low end of the scale, what we did. So the voltage, I'm going to use, actually I'm going to change pens. I'm going to use purple, or this magenta color, is going to represent our data points for the resistor value. This blue value is going to represent the data points for our tank circuit. So at each of these frequencies, let's label them in. So at 20 times less than our resonant frequency, the voltage drop of our resistor was at 51 and change, so pretty much 52 volts. So we can put a mark up there. Okay, the next one that we had across the resistor at resonance was at 26 volts. So it is sitting right there. And then at 20 times, it goes back up to the 52 volts. So we'll do this right here. So the graph that we have representing the voltage of our resistor goes like this. It's going to come down here and then back up and go that direction. So if we kind of look at resonance, we have the lowest output possible. So with that in mind, if we have the lowest output compared to what our input is, what type of filter would this be? Are we stopping a band of frequencies, or are we allowing a band of frequencies to go through the filter without attenuating? That's the idea, is what is our filter going to attenuate signals outside of the range that we want. So let's take a look. So with that, if you're looking at it, we are going low, so basically we're attenuating at this resonant frequency, which means we are putting a stop to those frequencies. And we have across our resistor, this would be our band stop filter. Because, we've got the data here to prove it, because we have the lowest signal across the resistor at resonance. So that's not what we want. For a pass, we want it to have the highest voltage we could get at the resonant frequency. So now, the other part we want to look at is, so now let's plot the graph of our Vout tank. So at 20 times less than our resonance, we're pretty much at 0 volts. Okay? At resonance, we only get up to just about 26 volts. And when we're 20 times our resonant frequency, we're back pretty much down at 0. So the curve that we have of this guy is here. So at some point, we're going to have pretty much 0 volts. So if we look at the highest point, with the highest point of the highest output is at our resonant frequency, that's going to give us a band pass. That's when we're passing these frequencies. Now, in all actuality, these curves aren't in very good relation to the scale, because they're probably going to look. This guy's going to look a little bit more like this and have a very narrow band. But the idea is the same. Is that at resonance, what are we getting? The maximum or the minimum across the component or the set of components. So because this is here, we have the highest frequency at resonance, or the highest voltage out, which is the most we could get. This is going to be passing our frequencies versus attenuating the crap out of them. So this one over here, where we're across our inductor and our capacitive, this is our band pass. Which, if we come back up and look, I'll go into the previous set of notes. We have a band pass is across our resistor and across the, where did it go? There we go. Across the inductor, the reactive components was our band stop. Across the resistor was our band pass, where now that they're in parallel, they've shifted, and across our resistor is now our band stop, and across our reactive components, it's the band pass. So anyways, like I said, these were for the series. These are for, if I get back to it, our two parallel components. So now the other thing that I want to kind of look at real quick, this is kind of tying in this last part as well. Well, I still have a little bit. I think this one's going to go just a little bit over an hour. It'll probably go about an hour 15, things like that. The last part that we have to do is we need to look at this circuit actually at resonance. And again, this, like I said, this is where the impedance of the tank circuit, that's going to kind of dictate things. We're going to see voltage drops. We're going to see things that coming in at the 45-degree angles, and that's what we should be seeing. So with our impedance of our tanks, we should be seeing these guys at 0 when they are way low, or like they're way outside of the scale. So either really, really, really low frequency, really, really, really high frequency, or they're also at resonance. We should see zeros on those as well. And so kind of continuing on a little bit, so we're going to look at two more frequencies with with the same circuit. We're going to look at our resonant frequencies, F1 and F2, and solve these guys out to get the impedance of our tanks. And so that's one way we can kind of determine that, and we're going to see those voltage drops across them. And they're going to be, again, around the 45 degrees for each of them. So, yeah, plus or minus 45. So let's go ahead and look at this real quick. So the last thing that we did is we have our resonant frequency. That is equal to 178,837 hertz. The Q point we calculated was 20.432. So that's not going to change compared to what we did that very, very first time when we solved the circuit. But now we need to know what is our bandwidth and what's our two new frequencies to solve at. So we remember we take our bandwidth is equal to our resonant frequency divided by the Q point. So we take 178,837. We divide that by the 20.432. That's going to give us a bandwidth of 87 53 hertz. So half of that going up and half of that going down is going to give us our two critical frequencies. So F1, FC1, whichever way you want to put it, is the 178837 hertz minus the 8753 divided by 2. So that's going to give us 174,461 hertz is this frequency. And our F2 is going to be the 178837 plus half of the bandwidth. And that gives us 183,214 hertz. So in the questions on Moodle, it's going to be asking us to solve for our resonant frequency, our Q point, asking for the bandwidth, and for these two frequencies. And you just have to put it in whatever format that it wants. I believe this one asks for it in kilohertz, so you'd have to put it in like this. But those are just easy conversions to do. When we're talking about the thousands, I don't like putting in the dot 3 decimal places in kilohertz. It seems kind of redundant to me, so I write everything out with the 6 digits. All right, so previously when we solved for this, the other one it's going to want to know is our impedance of our tank at resonant frequency, which we calculated it, and that came up to be the 55,238 at 0 degrees. So now we want to know, the last part is the Z tank at our critical frequency 1 and our critical frequency 2. Okay, so now let's go through and let's solve based on this value right here. So at critical frequency 1, which we solved for to be 174461. So what we need to do for is we need to solve for the capacitive reactance of our capacitor, the reactance of our inductor, the impedance of the inductor, and our Z tank. Okay, so X of C, remember, is 1 over 2 pi times the frequency times the capacitance. So we have 2 pi times 174461 multiplied by the 330 pico. Take the reciprocal of that, and that is going to equal 2764 at an angle of -90 degrees. We have the reactance of the inductor, so is 2 pi times the frequency times the inductor is equal to 2 pi times 174461 times 2.4 millihenries, and that's going to be equal to 2,631 ohms at an angle of 90 degrees. So now we have to come back and look at the impedance of this inductor, and so that's going to be the 132 plus J of 2631. We put that into polar. That's going to come out to be 2634 at an angle of 87.128 degrees. So now we got all this work done and we can finally solve for the tank circuit impedance. So remember, the impedance of the capacitor times the impedance of the inductor divided by the impedance of the capacitor plus the impedance of the inductor. And I know this is kind of a lot of talk and a lot of boring stuff, but the reason is there's just a lot of steps that we have to do to get through these guys. So when we come through there, we're going to have 2634 at -90 times 2764. Oops, sorry, I flipped those. So we have the 2634, which is at 87.128. That's the inductor, multiplied by the 2764 at the -90, divided by 0 minus J of 2764 plus the 132 plus J of 2631. So we calculate that all out. This is going to get converted. You add those together in rectangular, convert it to polar, multiply those two guys together, divide the two out. When it's all said and done, our Z tank is going to be equal to 38,853 at an angle of 42 degrees. And that's what we want to see, is the impedance of our tank at around 45 degrees when we're at our -3 dB point, which is our critical frequencies. We could continue to go on and solve this down to find the voltage drop across them, and then we have our max voltage, min voltages, things like that, and then we can put them in and we will see that -3 dB. But right now we don't need to go into that because we have done it a bunch of times. This is going to be no different than any of the other filters. That's one of the keys about filters, is that they will always be that -3 dB at the two critical frequencies, upper and lower end, if it's a resonant circuit, or just the one frequency if it's a regular high pass, low pass circuit. So we have this value that we're going to want to plug in for our answer. Then the last one we're going to be asked to find is the critical frequency 2. We want to find Z tank. So on that one is right here. So we have 183,214 hertz. So again, we're going to follow the same steps. We're going to find the reactance values for the capacitor, the inductor, find the total impedance of the circuit, and then we're going to find the impedance of the tank. So as we go through, so the capacitive reactance, 1 over 2 pi times the frequency times the capacitor. So 1 over 2 pi times 1.83214, 330 pico. That gives us 2632 at -90. The reactance of our inductor is 2 pi FL, and that's equal to 2 pi times 1.83214, and the inductor is 2.4 millihenries. That value comes out to be 2763 at 90. So again, we should see at the higher frequencies, we should see this inductor value climbing up. The capacitor should be decreasing. The impedance of the inductor is the winding resistance plus the impedance. So 132 plus J of 2763. We convert that into polar. That turns out to be 2766 at 87,265. So now that we have the impedance of our capacitor, impedance of our inductor, we use the product over the sum again. So Z tank is going to be equal to impedance of the capacitor times impedance of the inductor divided by those two added together. So we have 2632 at -90 multiplied by 2766 at 87,265 divided by the 0 minus J 2632 plus the 132 plus J 2763. So again, we're going to add those together in rectangular, convert that total into polar, and then divide these numbers, multiply the top two, divide by the second one. The final answer we come out to be for Z tank is going to be equal to 39,147, so 3,147 ohms at an angle of -47.517 degrees. And that is exactly what we should see. That's our double check. So when we come for these impedances at critical frequencies, they should be right around plus and minus 45 degrees, within a few degrees of that. And the Z tank at our resonant frequency should also be at 0. If we don't, that's kind of a stopping point for us to double check and make sure we've done everything else correctly up to that point. Like I said, the the thing we can do is at resonance, we're going to have those equivalents, and it makes it really easy to calculate it because everything else is going to fall away. But either way, that is an example of what we're going to be looking for on the homework. There's lots of steps to it, but in the end, what we have is these 8 circuits based on, what is their output doing to determine, is it a band pass, a band stop, things like that. So one of the last things I want to do is let's just kind of look at these guys real quick, and we'll talk about these again in their different styles, or different configuration to determine what they are. So the 8 circuits that we have our generator, we have a resistor, we have a capacitor. Our output is being taken across the capacitor. We have the opposite of that one, where we have the capacitor with the resistor, with their output being taken there. We have our resistor and the inductor with the output being taken there. And the last one we have of this style is the inductor and then the resistor with output being taken there. We also have the next set of circuits. We have the resistor followed by the inductor and the capacitor with the output being taken there. We have our capacitor, our inductor, and then the resistor, so with the output being taken across the resistor. And then we have our parallel versions, where we have our resistor and these and that, our V out, and then we have the opposite, where we have our parallel branch, capacitor and inductor in parallel with our resistor and that. So now we should be able to at least identify what these are: high pass, low pass, band stop, just based on their configuration and what we know about what they do. So remember, let's come back and look, and I'll label these in a different color. So the first circuit, I'll just number these. So we got 1, 2, 3, 4, 5, 6, 7, and 8. So in the first circuit, we have a resistor and capacitor. So as frequencies get higher, we're going to see a decrease in our X of C value. So if we have a decrease in our X of C value, we're going to have a decrease in the voltage out. So in this case, the higher the frequency, the lower the output. So which means this is going to be a low pass filter, because we want high voltages at our critical frequencies. Okay, so as this gets lower and lower, more voltage is going to be dropped across here, so the output's going to go down with the frequency going up. So we're wanting low frequencies to pass through the filter without being changed. This next one is the opposite. So we have our capacitor and our resistor, and again, let's look at the component that's going to be changing. So the X of C is, in this instance, is what's going to do it. So our X of C, again, it gets lower and lower based on higher frequencies. But if we go lower frequencies, this is going to get higher and higher. And so what this is going to do is at high frequencies, we want the highest voltage. So the highest voltage at high frequencies is going to be across this across our resistor, because this is still going to be dropping less and less voltage, which means it's dropping more here. Same thing it's doing on this one, but on this one, the output is going up and up as our frequency changes. So here, on the first circuit, remember, as our X of C, as frequency increases, the voltage out decreases because X of C decreases as frequency goes up. And this rule is going to stay the same for the 2 capacitors. In here, as frequency goes up, the voltage out is going to go up. So in this case, this is a high pass filter. Okay, now we're going to look at the inductors, kind of the same thing. What's my voltage going to do? So if the frequency goes up, the voltage out is going to go up, because This value, the X of C value of our inductor, or X of L value, as our frequency goes up, gets larger and larger, which means this is going to be taking more and more of the voltage. So with the output across the inductor, this is a high pass. So kind of the opposite of our capacitor circuit, where we take the output across the reactive or the resistive component. We're going to see these values. We're going to see those flip-flop. The opposite with circuit number 4, as our frequency increases, the X of L increases, which means the voltage drop across our resistor and our output is going to go down. So this is a low pass filter. Okay, we'll come back here to our resonant circuits. So when we have the resistor being played across these guys, so as we get a frequency that goes higher and higher, the inductor and the capacitor, those two are going to cancel each other out because they're going to be 180 degrees out of phase. So at our resonant frequency, XL equals XC. And since they're 180 degrees out, this is pretty much going to give us a 0 voltage out. And then as it increases, these are going to separate, and then we're going to start to see those capacitor, or one of those values get more and more depending on which way we go on the frequency. So just like we had before, the inductor is going to get large in comparison to this guy is going to get really small, so we're going to get more and more voltage coming across this guy. So 5, when we take the output across a series RLC circuit, this is going to give us a high pass filter. Oh, sorry, not a high pass filter. This is a band stop, because we're going to get the least amount of voltage at resonance, and then as we increase the frequency each other direction, higher or lower, eventually the resistor or the inductor is going to get larger than the resistor and start taking more and more voltage. The smaller we go on the frequency, the higher X of C is going to get. The higher the frequency we go, the higher the X of L is going to get, and therefore taking more of the voltage. So we have a band stop, because at resonance is going to be the least amount of voltage out. So on the other side, on 6, so if we take the output across the resistor, just like what we said, at resonance, this voltage across the inductor and capacitor pair is going to be almost non-existent. So with that being said, this is going to give us a band. Come on, I'm almost done. There we go. This is going to give us a band pass, because we're going to get the highest voltages out at our frequency, and then just up a little bit, just down a little bit, but then after that it's going to start rolling off. Now we're going to come to the parallel ones, which we just learned about. So in this case, when these guys open up at resonance, we're going to have the capacitor and the inductor is going to be very large, practically an open. We're going to have that equivalent resistor sitting here, and that's usually going to be a lot higher than our resistor in line, and that's going to give us the maximum amount of voltage. Because then once we start changing the frequency, because these two are equal at resonance, when we start changing it, one's going to get large, one's going to get smaller, and because they're in parallel, it's going to drift to the lower of the two. So then if we have a low resistance compared to a higher resistance, or compared to what it was at resonance, the voltage out is going to go down. So with our reactive components in parallel against the resistor with the output taken across them, this is going to give us a band pass, because this is the highest voltage that it's going to get, and then at the up and down frequencies, this is going to get lower and lower. And then the same is true here. So again, with that, as we're changing this value, we're going to see these change. We're going to get a lower voltage here at low frequencies, low voltage at those, and then a higher frequency at resonance. So this is going to be our band stop. And like I said, well, those are the ones we just did. So there's kind of a little quick and dirty comparison on how we can look at these guys, and all it's based on is, what is my reactive component doing? How is it reacting to the frequency? Is the resistance going up or down, or the reactance going up or down of that component based on the frequency? And then where's my output being taken? And so we can logically work through all these different types of filters, even if we didn't have any values. Not a single one of these we had a value. We just took into what the reactance was doing to solve for them. And so with that, we can be able to determine what type of a filter it is just based on what is my X of C doing. So you can memorize these if you really want to, but just kind of take the analyzing tool and use that to solve for these circuits. What is my output doing, or what is the component that my output is taken off of? What is it doing based on the frequencies? And the resistor, like we said, is not going to change at all when we get going. And so the only thing we have to worry about is just the reactive components. So anyway, with that being said, that's what we have, and that is all the videos that I have for this week. Um, Again, I'm going to have the test and everything due on Monday night at midnight, not Sunday. So we're going to kick that out another day as well. That way, it gives you guys a chance all day tomorrow to work through these, work through the labs. Labs are going to be due Monday night as well. Give you guys over the weekend to process and assimilate all this information. Um, I think that's probably going to end up being the standard. But anyway, so that's what we're going for with this week. Like I said, test will be due Monday night, lab will be due Monday night. It gives you the weekend to finish everything up. If you do have questions, please feel free and call me, let me know. I'm sorry this was a longer video. I probably could have split it off there at the end, but I just didn't want to create a 10-minute video to explain this last little section. And again, like I said, there's kind of the quick little snapshot. We'll leave you with that. And then anything you guys have or need, please feel free and let me know. Next week, I think one thing I want to do is I want to have a chat with each one of you guys just to check in and make sure everything's going good with you. You need anything. So I'll send out some emails about what times we're going to do that. Like I said, it's just kind of a quick little one-on-one just to make sure you guys are okay. You're getting the information done and just kind of check up on you. Make sure you guys are doing okay. One of the complaints that we had was that some students are feeling that the professors are not communicating with them very well. Um, I apologize if I've fallen into that category. I hope I haven't. I thought I've been able to, with these videos to communicate with you guys at least the information that's needed. But like I said, it's just to check in to make sure you guys are doing okay and make sure that you guys know that you have open communication with me. If you do have questions, please feel free and let me know. I know there's some teachers that I've had that are hard to get a hold of. You know, you'll send them an email and you'll get a response 2 or 3 days later. Um, things like that, and especially with this where we're not seeing each other at all face to face, it makes it hard. Um, I get it. So like I said, please, let me know and I'll send out the schedule for those next week, just to check in with you guys and make sure everything's good. With that, I don't have anything else. So as always, be safe and enjoy the rest of your guys this week.